Hey y'all, Data Guide here. And to celebrate the recent release of Meta's open source Llama 3 model, which is just an exceptional large language model for a variety of tasks, I want to show you how you can use its API and incorporate it into a script that takes all the public docs for a piece of software. In this case, going to use Apache Airflow, processes those, vectorizes them, and then uses the Llama large language model to perform retrieval augmented generation. So making it easy to query and ask those documents very specific questions and receive human readable answers. So just really think this is a cool use case that pretty much anyone can make use of. And I think Llama 3 is a really cool model, and I love that it's open source. So wanted to make this video. So without further ado, let's get into building. So to start building our script, we're going to do, as we do in almost every single script we build, is import a whole series of different packages and requirements. So here we have first requests, which allows us to request from APIs, pull data, then interpret those requests, responses. Beautiful Soup, this is a really, really great tool for scraping web pages and basically using the results within Python scripts. Here, transformers, so this is the Llama tokenizer, Llama for casual ML, pipeline, we have the sentence transformer for interpreting sentences. So these are basically the different ways that different tools Llama provides for tokenizing data, so turning it into vectorized numbers from just the raw text that we're going to get from the docs. Then we also just have this Llama for causal ML, so for predictive large language models, and then also creating a pipeline so we can create different steps within this process of getting the data, querying it using large language model, and serving the end response to our end user. Then we have FAISS, which is another thing from Facebook. It's a library for allowing you to perform efficient similarity search and clustering of dense vectors, so allowing you to search your vectorized data after we vectorize with the tokenizer. NumPy for NumPy arrays, so pretty classic data tool within Python. Then we also have OS for interacting with the actual operating system. URL lib parse for creating URLs, joining them. And then we also have TQDM. This is a fun little thing that allows you to see a progress bar when we're iterating through a loop. So in this case, going to be iterating through the different pages we're collecting from those Airflow docs. So now the first step we're going to create, first function of the script, is just going to be a function to get all of our links. So here we're just going to use the request library to send a request to our base URL, which we'll define later. Use Beautiful Soup to parse in the HTML parser Beautiful Soup provides to parse the response content, find all the links, so basically pull the different links for this URL, then join them to create our full links to get just the HTML page that underlies it, and then return an array of full links. So basically what this is going to do is fire off at our Airflow URL, figure out how many URLs there are that we need to actually query from, and then build links to query the HTML endpoints for all of those. So then our next step is going to be actually scraping those pages. So here, define scrape page. So for these URLs that we're feeding in, send a request to get the contents of that URL, raise for status. So there's an error, just send a status and throw that into the operating system so we know what's happening. Then we have Beautiful Soup, which is going to parse the actual content of the individual pages within the documentation, find the paragraphs, join all the text, and then return some slightly cleaned up text from each of those HTML web pages. And then obviously another just kind of error logging system here for in case there is any errors. Next, what we'll do is build our base URL. So here we have our base URL, which is going to be just the Apache Airflow index of all of the different pages we'll have. Then get all links, so feeding in that base URL, getting all the different pages that are included in that index, and then having this for loop go through, iterate through every single one of those pages, and then return those all into the document text array. Then what we'll do is pre-process that text. So the next step is going to be whatever kind of cleaning you want to do on your text. So I'm just going to keep it pretty basic right now, just kind of strip out any blank spaces, replace any null values, and then just give me the cleaned up raw text. You don't need to clean it up too much because at the end of the day, we're just feeding this into a large language model, so we don't actually need to really understand it too well. And if you clean it too much, we might actually lose some valuable information. And then we're going to run this as a loop again. So for each of these raw doc texts, convert those into our pre-processed text, function and then return them out into this clean docs array. Then, so we have all of our different pages. They're all a bit cleaned up, all ready to be actually processed and queried. So, or not processed, they're ready to be processed, not queried. So next, we're going to load our LLAMA tokenizer and our LLAMA model. So just bring in default LLAMA 3 model for the tokenizer and for our actual large language model. We're also going to bring in our sentence transformer, which will allow us to interpret sentences and also output kind of more complete human sentences. And then once we're done with that, so we have our toolkits in place to actually use the LLAMA large language model. So now we can actually start doing our machine learning stuff. So first, we're going to need to split those documents into smaller chunks. So we'll just have them be 500 characters per chunk, store them all in this array. And then for every doc in clean documents, so kind of a double loop here. So for every document, and then for I in range, so just chunking through each individual document page and creating those 500 character chunks to make it easier for transforming down the line. And then also, kind of other thing I'll have this, if you're running this in something like Spark or distributed computing, this would also allow you to distribute these processes across multiple different compute nodes. Once you have the pre-processed chunks, you can have those then all processed in parallel. So then for embeddings, what we'll do is use the sentence model to encode the different chunks. So this is going to take all of our individual chunks, use that large language model to encode them as sentences, understand them, and then save them as vectorized embeddings. Then what we'll do is create our embeddings and just save them to our disk. So here, what this is going to do, numpy save, embeddings.numpy, chunks.numpy, and then here, set that array. Just go through all of the different arrays of chunks and save them all as individual files. And then the next step is to search those vectors. So here what we'll do is we're going to load our embeddings array, so load that file of embeddings. Then we're going to add that as a dimension to our embeddings array, or add a dimension to our embeddings array. Then use set an index, so FAS. So this is actually going to search our vectors and convert them into. So essentially what's happening here is we're just loading our embeddings into a compatible format, so just an array that then FAS can eventually search. So here, adding these all to this index, so the embeddings array, so going through, so we create our index and then we add our embeddings array to that index. And then what this is doing is giving FAS an index that it can then search to actually find, retrieve our different text chunks, and then also you can further tweak this if you want with different FIS parameters, different search algorithms, even further down the line. So now that we have our data all in a format that's really easy to query, we actually have to enable the retrieval of that data. So here, what we're going to do is define a function for retrieving any relevant chunks. And so here, what this is doing is enhancing the response generation by concatenating different retrieved chunks to form a contextual response. So this basically, instead of kind of force the model to go through all these individual chunks, which might not actually make sense, this will help improve the model's ability to generate more coherent and relevant answers because it has everything available in one concatenated location to search through and query. So nice little feature there, or functionality there, just to make sure that, hey, this is going to give me the most accurate responses as possible by giving the model all the context it needs for a particular query. Then once we've done that, retrieve the relevant chunks, we're then going to actually generate a response. So here, what we're doing is joining the different chunks within the retrieved chunks. So taking our relevant chunks that we're going to need for this response, then building them into our input text. So you can see taking that context and then using Ginger templating to put that into our question. And then also we have our generator. So the generator is going to take that input text to give me the max length of the response, number of return sequences 1, and then return me a answer to whatever my question will be. So this response, or this function, takes in a query, takes those retrieved chunks, uses the large language model to query that concatenated set of chunks for generating a response to whatever my question was. So that's really kind of the crux of this script and puts it all together. So now we have our response getting thrown back. We have all the different pieces in place. we're going to need to generate a pipeline now to actually put everything together. So here, generator pipeline, just call it text generation, use a large language model we defined before, LLAMA, and the tokenizer we defined before. Then we're just going to load a little example query here. So how does Apache Airflow handle scheduling? Then what it's going to do is pass that query to retrieve relevant chunks for my particular question, and then generate a response using the query and those retrieved chunks. And then we'll just print that out to our command line, and boom, printed response, generate response, whatever the response is from the model. And then we're also just going to add some error handling functionality as well here to make this a really complete production grade script. So first, define safe scrape. So what this will do is just return, either run this scrape page function, but if there is a failure, just return a failure here, print it to our logs. And then also, we're going to want to wrap kind of the final response into a function or API. So here, this is where we have our actual answer query. So this is making it really deployment ready, because now we have a wrapped process where you can just say, hey, all you need to do here is insert a query, and all the different other functions of the script will take care of the rest. So it'll go find those relevant chunks, it'll then generate the response, it'll scrape the pipeline or scrape for any relevant pages. All the end user has to do is just fire a query. And so you can fold this into an API or into a larger system where someone can just enter a query in here and get a response that has been augmented by all the different documents that you want to feed into it. Then just some additional things you might want to add for actually doing multi-processing. So I mentioned before, like the advantage of something like this is you can process all these chunks in parallel. We also can import multi-processing and then run this scrape all. And what this will do is create a pool of workers to scrape all those individual pages in parallel. So instead of needing to actually have that run sequentially, which can be just prohibitively long, you can spin up a pool of compute nodes and run those all in parallel. That is all I have for you today. I hope you found this helpful. I hope you've given you some inspiration for a future project, and I hope you have a great rest of your day. Data Guy out.